electronics. This is a video on the part 2 of logic gate problems. So I've uploaded a video on the part 1 of logic gates concepts and numericals. This is a part 2 of that video. I've been receiving a lot of requests to do the video on the part 2, including more problems. So here it is. So in this video we'll be seeing more numericals on the logic gate simplification. Okay, so this is very much important if you're going for any of the competitive exams related to electronics. So if you are anybody who is preparing for the competitive exams of electronics, please do watch this video till the end. Okay, so the first question is, the output of the circuit shown below is dash. So this is a circuit given. This circuit consists of 3 gates basically. These 3 gates are identical gates and they are XNOR gates. Okay. So these are XNOR gates. We have already discussed in the first video on the part 1 about the basics of the expression, the truth table and the output expression of the XNOR gate. So here we are going to do some problem. Okay. So here if you see, the input of the first XNOR is A B bar and the second XNOR is A bar B. And this outputs are being again fed to another XNOR gate. Okay, so how can you write the expression, output expression for this particular logic circuit? Let this output be Y. So the Y will be is equal to, you can write in simple terms of XNOR, that is A XNOR B bar, again XNOR A bar XNOR B, right? So this corresponds to your first gate. This corresponds to your second gate and this XNOR corresponds to the last gate, which is the output, that is the output gate here. So there are 3 XNORs, right? So I've written a simple expression to constitute this circuit. So here you can see this is A XNOR B bar, XNOR A bar XNOR B. So using the associative property, which is a famous property in digital electronics or in Boolean simplification, you can write this as A XNOR A bar into XNOR B bar XNOR B. This is called associative property. Okay. Here what we have done, we have taken the A and A bar common. Sorry, we have taken the A and A bar together and put it as a single XNOR, and B and B bar together and put it as a single another XNOR, and total and taking both there is another XNOR. So this is the term. Now what is A XNOR A bar? It is equal to 0. How will it be equal to 0? I'll write the expression for A XNOR A bar here. That is A XNOR A bar is equal to, what is the expression for simply A XNOR B? It is A bar plus A bar into A. Right, I'll write the expression, this common expression for XNOR once again here, just to make you remember. That is, if it is, I'm going to write the general expression, okay. A XNOR B, if we are going to expand, it will be AB plus A bar B bar, right? So this is the general expression. Here B is A bar. So first term is both these terms, that is A into A bar, plus taking the complement of both. It will be, if you take the complement of A, it will be A bar. If you take the complement of A bar, it is A, right? So you will get the expression like this for A XNOR A bar. What will be this term? A term and its complements product is equal to 0. A term and its complements product is equal to 0. So 0 plus 0 is equal to 0. 0 plus 0 is equal to 0 is the output of A XNOR A bar. So here it is 0. Again XNOR 0. Right. So 0 XNOR 0 is, what will be the result? I'll write it here. 0 XNOR 0. That is 0 into 0 plus 0 bar into 0 bar. What will be this? 0 into 0 is 0. 0 bar means 1 into 1. So what is the value? 0 plus 1 into 1, that is 0 plus 1, which is equal to 1 is your result. So when you are seeing the 0 x naught 0, don't write 0, just try to do it. What will be the result coming? Then see the options. So correct answer is option B. 1 is your answer for this logic circuit. So this is actually very simple circuit. You only need to know one thing, that is the output of A x naught B. You should know. And also here you should know the associative property. Otherwise, if you don't know the associative property and if you go on writing the equations, it is a very lengthy process, right? So if you are first writing the expression for this gate, then this gate, and then giving to this gate, it is a very, very complex thing, right? Rather than just go on writing the common expression in terms of x naught and try to apply the any Boolean law if possible, try to apply it. Here if you see, you can apply associative property or associative law, and thereby you will get the answer is equal to 1. The next question is, the output of the logic gate in figure is dash. Here again, this is another XNOR gate. There is only one input, another input is being grounded. You need to find the value of output F. Simply write the expression for XNOR. Here it is, the common expression is A XNOR B is equal to AB plus A bar B bar. Right. Here A XNOR ground means 0. Okay. So A into 0 plus A bar into 0 bar. Right. A into 0 is 0 plus A bar into 0 bar is 1. So A bar into 1 is equal to A bar. So the output is A bar is your output. So the correct answer is option C is your correct answer. That is the output for this logic gate F is equal to A bar. Okay, let us do the next question. The minimum number of 2 input NAND gates needed to realize Z is equal to A, B bar, C. Assume A, B, C available individually. That is, we are not getting the product term, we are getting the terms, that is the variables A, B and C are available individually. So what is the result? That is how many 2 input NAND gates you need. Option A 2, option B 3, option C 5, option D 6. So how many number of NAND gates you need to realize this expression? Okay, what I'll do is I'll remove this and I'll try to write it above. So in order to realize this expression, if you see what is the expression here, what is the expression here? Expression is Z is equal to A into B bar into C is your expression, right? So if you see this expression, we need to realize this using NAND gates. NAND gates means they are actually AND gate plus a complementary gate, that is a NOT gate, right? So what I will do is I will take the both variables which are not in complemented form together and one variable which is in the complemented form, and we will try to realize it separately because it is a NAND gate. I am talking like this because here there are 3 variables. 2 variables are in a non-complemented form, that is A and C, whereas B is in the complemented form. Okay, so we will try to realize this A and C together and B together, and then we will combine. Okay, so what gates we need? We need NAND gates. A and C here, applying to a NAND gate, the output will be A into C bar. Okay, we need it as in a non-complemented form, that is we need A and C itself for this expression. So what we will do, we will take another NAND gate, we will short its input and we will try to apply this to that NAND gate. So the output is now AC. Okay, now we have AC in our hand. Okay, now next we need B bar. So it is very simple. You can take that and short the input of another NAND gate, apply it to that NAND gate and you will get B bar. Right. Now we will try to give this to another NAND gate, that is 2 of this, AC and B bar we will give. And what will be the output? AC, B bar, the whole bar, right? So we have our expression, but now this is in the complemented form. Again, we need to remove that complement. So what we will do, we'll take another NAND gate, short its input and apply this. So the last stage we will do this. So our output will be A, B bar, C. So this is how you can realize this expression. So this is very simple, but you need to think how to realize this. If you look at your expression, I have already discussed many questions like that is the number of NAND gates required to realize expression. You can apply either Boolean simplification, either double complemented form, De Morgan's law, or you can convert SOP to POS form. So here if you see, this is a very simple expression. It is having only one term, that is a product term. So you can think of directly realizing it. But while thinking, you should know that you need to realize with the NAND gate, right? NAND gate means AND gate plus NOT. So this NAND gate originally will give us a complement. That is, if you give A and C, it will be producing a ASC complement. So in your expression, if you see, two variables are in the original form, that is AC for AC. A and C are in original form. B is in the complemented form. So we cannot really realize A and B together because one is in the original form, another is in the complemented form. Also, we cannot take B and C together because again, one is in complemented form, one is in the real form. So what we will take? We will take the two variables which are in the original form together and the complemented one separately. And if you start doing this, you can very easily complete your answer. It is AC, we will get AC bar, we need originally AC. So we'll again take a NAND gate, short its input. You can apply this to the input of this shorted NAND gate, you will get an AC. Again, through this path, you can realize B bar. Again, you will get a complemented form of your required expression. Again, take another NAND gate, short its input and apply. And you will get your correct answer or expression. So how many NAND gates are here? 1, 2, 3, 4, 5 NAND gates you need. Okay. So the correct answer for this question is option C. 5 is the correct answer for this question. What is the output expression of the circuit given below? Okay, so this circuit consists of a NAND gate, OR gate, AND gate and the XOR gate. First thing is that you should be able to identify the logic gate. That is very much important. If you have to at least attempt this question, you should be able to identify which gates is present. That is, you should be familiar with the symbol of each gate. Here it is NAND gate, OR gate, AND gate and XOR gate. So you need to find the output of this circuit. Output is represented by M1. And here the options are given in the form of the expressions for M1. Okay, by looking at the options, one thing is clear that last term is constant. That is XOR R, XOR R, XOR R and XOR R. Here R is our third variable. So if we find the expression of this much of the circuit, you can answer this question. Okay, so what is the expression of this much of circuit? You are being given two variables P and Q. P and Q is first fed to the NAND gate. Again, this fed to the OR gate. Then taken the product of the two outputs. Simple, right? So what will be the expression for NAND gate? It is P into Q bar. Right? Then into, because here it is a product. So into, what will be here? Here it is P plus Q. Right? So this is your expression. Now if you see here only one that is one gate or one expression is being used, OR, AND, NOR or XOR. So you need to find in that way. What will we do here? We will try to apply De Morgan's law. So what is De Morgan's law for P into Q whole bar? It is P bar plus Q bar, right? So P bar plus Q bar into P plus Q. Now expand these two brackets. You will get P bar into P, it is a 0, plus P bar into Q, P bar into Q, then plus take this Q bar and multiply inside the bracket. So Q bar into P plus Q bar into Q, that is again 0. I am just expanding this bracket, that is I am just opening these two brackets by multiplying the terms inside. Okay, so this will be your expression. That is P bar into Q plus Q bar into P. What is this expression? This is nothing but P XOR Q. Right? That is simply P XOR Q is written here. So what is our expression? It is P XOR Q. Then again last term is XOR R. This is your expression. Okay, so which is your correct answer? Correct answer is option D is your correct answer. That is P XOR Q XOR R is your correct answer. So I hope this is clear. So this is again another type of circuit you can face in a question paper. I'm not saying the exact circuit, but this kind of circuits. I have not included any of the simple questions in my video. And that is if you go for examination, you can also find questions like I'm talking about the technical assistant examination, because in scientist examination you cannot find really very simple question. That is, you can also find circuits like this. What is the expression for this? Okay, so if it is A, B and C, what will be the expression? It is A, B, then into, sorry, C and D. A, B into C plus D, right? This is the expression. That is, here it is a AND gate, so it is a AB. Here it is a OR gate, so it is a C plus D. So output is that both the outputs are fed to a AND gate, so it is a into. So this is the expression. So this type of questions can also come in your examination, but I have not included that sort of questions in this videos, because that sort of questions mostly people will be able to solve. But this type of question, that is how many number of NAND gates you need, that is what is expression for a little bit complex circuit, it is difficult to answer. So I have tried to include that in part 1 also and in part 2 also. A minimum number of 2 input NAND gates to implement this function. Function S F equal to X bar plus Y bar into Z plus W. So what I'm going to do is, here there is one expression called X bar plus Y bar, right? That is, we know that XY, the whole complement, is written as X bar plus Y bar. According to which law? It is according to De Morgan's law. So according to the De Morgan's law, you can write this. Here we are being given this X bar plus Y bar. So we can write it in which form? X, Y, the whole bar, right? So I'm going to replace this term with, that is, I'm going to write F first, X, Y whole bar into Z plus W. Okay. Now I'm going to multiply this X by the whole bar inside the back bracket. So I'll be getting XY bar Z plus XY bar W. Okay. Now I have this expression in my hand, that is XY bar Z plus XY bar W. Now I'm going to realize this using NAND gates. Let us see how. The first term is XY bar. It is very simple. So you only need one NAND gate for this. X and Y is fed as input, and this NAND gate will give a XY bar. That is our required expression. Then now I'm going to apply this to another 2 NAND gates, because I need 2 other variables, right? Along with this term I need an Z, and along with this term I need a W. So I need to feed this to another 2 gates. Okay, one gate I'm going to apply here a Z. I'm going to apply a Z to that one NAND gate, and for the second NAND gate I'm going to apply a W. Okay, so what will be the output? Here it is X, Y bar Z the whole bar and X, Y bar W the whole bar. Right. Now here I have this term and I also have this term. So I have my term which is required. Originally is I need what? XY bar into Z. I don't need this complement. Here also I don't need this complement. So in order to remove that complement, what I'm going to do is I'm going to feed this. I'm going to feed this to another NAND gate. What will be the expression here? It will be XY bar Z whole bar into XY bar W whole bar, the whole bar. Sorry. The whole bar, right? So here we need this expression and the output is this. According to the De Morgan's law, here again you are getting what? X, Y, the whole bar. So you can write it in the form of, that is, if you have xy bar, you can write it as x bar plus y bar, right? So I'm going to write this expression as x bar plus y bar form. How will it be? That is xy bar z plus xy bar w. This is your actual expression. If you solve it, you will get this one. So this is actually our required expression, right? So this is just by applying De Morgan's law, you will get our required form of expression. So this much of NAND gates you need to realize this expression. Okay. So what is your answer? How many NAND gates you need? 1, 2, 3 and 4 NAND gates you need to realize the given expression. Okay. So the correct answer is option B, which is 4 is your correct answer. Okay, so these are the questions which I have included in this video. You will be facing a lot of questions like how many NAND gates you need, how many AND gates you need, how many NOR gates you need. Mostly from NAND gates and NOR gates, because they are the universal gates, right? You can realize any expression using NAND gates and NOR gates or the universal gates. Okay, I hope this video was useful for your preparation. I hope you gain some knowledge from this video. I hope you get familiarized with the logic gate simplification a little more from this video. If yes, please do give it a thumbs up and also share this video with all your friends. And if you want more videos, please do subscribe to the channel.